So what we see in front of us are a series of problems where we are going to have to expand a binomial, meaning we've got some binomial that's being raised to an exponent. Now, for the first one, for example, x plus y to the 0 power, it's pretty easy. Anything raised to the 0 power is 1. So no matter what x and y are, whatever they would add to, raising it to the 0 power is going to be 1. Or in the case of the second example, x plus y to the first. Well, when you raise something to the first power, it's just itself. So we just have x plus y. Even x plus y squared isn't too bad. What we have to do is we have to FOIL that out. So I'm going to actually do that off to the side here. So I can't distribute the exponents. Exponents don't distribute. We've heard that a lot. Instead, what we have to do is use our FOIL technique to multiply. And so I'm going to do exactly that. So I get x times x, which is x squared. Then my outer and inner terms are two of the same thing. I get an xy for the outer term. I get a yx or an xy for the inner term. And then finally I have y times y, which is y squared. So if I gather my like terms, I'm going to get x squared plus xy makes 2xy. Notice the exponents don't change when we add and subtract, just the coefficient front changes. Think of this as 1xy plus 1xy makes 2xy. And then finally, plus y squared. So that's our answer here. So we get x squared plus 2xy plus y squared. And then to get to x plus y to the third, it's not terrible. We just have to take this answer that we have right here. That would be x plus y squared. And then I just have to multiply it by x plus y one more time. So by increasing the exponent by 1, I just have to multiply one more time. And so if we do that, I just need to make sure everything from the first set of parentheses multiplies everything in the second set. So we can roll through and get x times x squared, which is x cubed. Then we can multiply this x squared times y, so we'll get an x squared y. Then I need to do the same thing with the middle term. So the 2xy multiplies the x, so I get 2x squared y. And then I need that 2xy to multiply the y back there, so I get 2xy squared. And then finally I have to make sure that y squared multiplies everything. So I've got y squared times x gives me plus, we'll go in alphabetical order there, so plus x y squared. And then finally the y squared needs to multiply the y at the back, so I get plus y cubed. And so our answer, after we gather our like terms, is going to be the x cubed term first. Then I have an x squared y and a 2x squared y. So together, 1 plus 2 makes 3x squared y. Then I have plus 2xy squared plus 1xy squared. So I get plus 3xy squared. And then finally, I have my last y to the third. So that wasn't terrible, but it was pretty bad. And the next two would be even worse, because now I'd have to take this answer and multiply it by x plus y through a whole FOIL type process, and then I'd have to do the same thing again. So what would be nice is if we had a shortcut to be able to perform this, and in fact we do. So that shortcut takes advantage of something called Pascal's triangle. So Pascal's triangle is just a numerical pattern that we see in front of us here, where we start from the top of the pyramid. The top of the triangle is 1, and then you can see running down the left-hand side and running down the right-hand side, it's just 1s all the way along. And then in the middle, we have what seems to be a random collection of numbers. But in fact, there is a pattern here. And the pattern is, if you take the two numbers above a number and add them, you get the number that, below. So for example, 1 plus 1 adds up to 2. 1 plus 2 makes 3. 6 plus 4 makes 10. 10 plus 10 here makes 20. So we could continue, we could expand this. If we wanted to make a row 7, we'd start with a 1 here, then from above it. 1 plus 6 makes 7. 6 plus 15 makes 21. 15 plus 20 makes 35. 20 plus 15 makes another 35. And then we can see that we have the same numbers on the back end here as we did at the beginning, 7, and then finally finish with the 1 on the outside. So what does this have to do with our binomial expansion? Well, these numbers in each row, and I'll make sure to highlight the fact that we start from row 0. The top of the pyramid, the top of the triangle, is row 0 rather than row 1. But each of those rows corresponds to the coefficients in front of all the terms of the binomials that we just did on the previous slide. So for example, if we take a look at row 2, row 2 here has 1, 2, 1 as the three numbers. If I go back to the previous slide and I look at x plus y squared, what are my coefficients in front of all the various terms? 1, 2, and 1. If we jump back to our Pascal's triangle, and now if we take a look at row 3 here, we can see we've got 1, 3, 3, 1 as our four numbers in that row. If I go back here and look at the x plus y to the third that we expanded when we were all done, what were the coefficients of our final result? 1, 3, 3, and 1. So the rows of Pascal's triangle predict what the coefficients are going to be in front of each term of our expanded binomial. So that helps us with those coefficients in front of each term, but what about the exponents on the variables? Well, if we go back, those follow a pattern as well. And so we'll take a look at this row right here, this x plus y cubed. If we look, the exponent on the x in the first term matches the exponent on the binomial in the unexpanded version. So x plus y cubed, the first term is x cubed. Then the x's just go down by one exponent in each successive term. So I start with x cubed, matching the 3 that I have here. Then I have an x squared term. Then I have x to the first. Remember there's a 1 there even though we don't write it. And then the last term is missing the x entirely. So we're just counting down on the exponent of the first piece inside the parentheses from the first term, x to the third, down to x squared, down to x to the first, and then the x is missing in the last piece. Now on the other hand, the second piece in the parentheses, the y, is counting in the opposite direction. So there's no y in the first term. We have y to the first in the second, we have y to the second, and then we finish off with y to the third. So the two pieces inside the parentheses, the x and y, are just counting in opposite directions, starting or ending with the exponent on the original binomial. And so then, if we have those exponents coupled with the coefficients on each of those terms from Pascal's triangle, we don't need to mess around with any of this FOIL that we did earlier to generate the answers for this type of question. So if we go back to our example here down on the bottom, if we want to find what x plus y to the fourth is, I'm going to first start with the exponents on the x's and y's. So I'm going to leave kind of like a blank for the coefficient, and then I'm going to start with the exponents on the x's and y's for each term. So I'm going to have x to the fourth, because we start off with the x with the same exponent as what's on the binomial, and then the y is missing. Then I'm going to have plus, I'm going to need a coefficient there, and now my x's are counting down in their exponents while the y's are counting up. So I'm going to have x to the x to the third, counting down, and then y to the first, or just y. Then my next term, again, I'm going to leave a blank there for the coefficient. I'll go back and fill those in a moment. So the next term is going to have x to the fourth, x to the third. It's now going to be x squared, and then the y's are counting up. There's no y, there's a y to the first, so now there's a y to the second. Go again, leave a blank there. So we've got x is now fourth, third, second, just x to the first, and then the y's are counting up, y to the 0, y to the first, y to the second, so we're up to y to the third. And then our last term, the x is now going to be missing, the y is now at y to the fourth. And if you'll notice, the exponents on each term always add up to 4. So here we see x to the fourth, here we see x to the third and y to the first, so those add up to 4, 2 plus 2, 1 plus 3, and then finally the 4 in the back end. So for x plus y to the fourth, our exponent, combined exponent on each term is also going to be 4. So the last thing I need to do is fill in my coefficients in front of each of these terms. And so I'm going to fill those in by looking at row 4. So if I jump here to row 4, I can see my coefficients are 1, 4, 6, 4, and 1. And so now I have the answer to my expanded binomial without having to do any FOIL. It's just x to the 4th plus 4x to the 3rd y plus 6x squared y squared plus 4xy to the 3rd plus y to the 4th. So if we look at one more where it's just x plus y in the parentheses and then some exponent, this time 5 on the outside, I'm going to approach it the same way. So I'm going to start off leaving the coefficient spot blank, x to the 5th in the first term, plus, I'm going to leave the spot blank, x to the 4th, y to the 1st. So my x's are counting down, my y's are counting up, but the combined exponent on the two pieces for each term is going to be 5 to match the 5 on the outside of the original binomial. So plus, I've got a space, x to the 3rd, y squared, plus, I leave a space for the coefficient, now it's x squared, y cubed. Again, the pattern continues, leave a space for the coefficient, x to the 1st, y to the 4th, and then finally, my last term, the x's are gone, and I just have a y to the 5th. And so now if I go back to Pascal's triangle, I'm going to look at the coefficients here in row 5. And so if I go back and fill those in, I'm going to have 1, 5, 10, 10, 5, 1. And so here's our answer. So we can see that this is a much faster approach than if we had used FOIL on repeat a total of 5, to multiply a total of 5 x plus y's. Instead, we're just grabbing coefficients from Pascal's triangle to make sure we use the appropriate row, and then we just have a numerical pattern on the exponents on the two pieces, x and y, going up and down respectively.